Click logs can tell you whether a new ranker helps, but only if you correct the bias. I will use PyTerrier and IPS in Python to estimate wins before an A/B test. This is the workflow you'll know how to run when we're done, which learns from past clicks and predicts whether a new ranking helps. I'm Professor Pi, teaching search and IR with simple Python. Search teams face a common dilemma. You can run an A/B test to compare rankers, but live tests are costly and risky. Clicks tell a story, but they are biased by position and exposure. Counterfactual evaluation aims to read old clicks and estimate how a different ranker would have done, without exposing users to risk. PyTerrier is a compact toolkit that makes indexing and retrieval easy in Python, so you can prototype this counterfactual workflow fast. At a high level, we want to use logged impressions and a small model of how likely items are to be seen to undo bias. The key idea is inverse propensity scoring, which reweights clicks by how likely an item was shown. That gives us an estimate of click rates under a new ranking rule. Strengths include no live traffic and simple math. Weaknesses are that variance can be high and propensities must be reasonable. We will build a tiny example. We will index 3 short documents, record a small click log, write a simple inverse propensity weighted estimator, then compare a changed BM25 configuration. The code is small and focused, so you can see how IPS corrects rank bias before you ever touch production. Now we will create the tiny index and run a baseline retrieval to confirm everything is live. This snippet initializes PyTerrier, builds a tiny index, and runs a BM25 search for one query. The variable docs holds 3 short documents with concise identifiers. The object index ref is created by iterdict indexer, which writes a small on-disk index that batch retrieve can query. The transformer BM25 uses the Terrier BM25 model, and Q provides a single query with a QID and text. Calling transform on BM25 returns a data frame of ranked results with scores and ranks. We then select the top row to display the winning document and its score. The printed top document confirms the index is live, and our BM25 retrieval is working. Next, we will construct a minimal click log and compute a naive rate and a propensity weighted rate. This example creates a minimal click log and computes a naive click-through rate and an inverse propensity weighted estimate. The data frame clicks records which document was shown at each rank and whether it was clicked. The dictionary P stores position propensities for ranks 1 to 3, and we attach those to each row as the column P. The variable naive is a simple mean of clicked, which is biased by position effects. The IPW estimate divides each click by its display propensity and averages over impressions to counteract rank bias. Lower propensities increase weight and variance. Higher propensities dampen corrections. The printed IPW rate is higher than naive, reflecting debiasing. Now we will create an alternative BM25 configuration and score how that new ranker would have performed on the same logged impressions. This code builds an alternative PyTerrier BM25 with different K1 and B, then estimates its CTR at 3 from old clicks via inverse propensity weighting. The object A is a batch retrieve configured with updated BM25 controls to produce a changed ranking. We call transform to get errors, the alternative results for the same query Q created earlier. The series top K selects the top 3 document identifiers from this new ranking. We align these documents with the logged clicks by indexing the clicks table on DocNo, retrieving their click labels and propensities. The variable CF computes the off-policy CTR at 3, by summing clicked over propensity and normalizing by k. The printed value estimates how the new ranker would have clicked without a live test. Next, we will reduce variance with a self-normalized variant and make a reusable helper to compute IPS at arbitrary cutoff. This snippet applies self-normalized IPS to reduce variance and also defines a helper to compute IPS-K later. We first select the logged rows for the alternative top 3 documents and compute weights as inverse propensities. The vector W is clipped at the parameter clip to tame large weights that cause instability. Lowering clip reduces variance at the cost of bias. The value SNIPS is the ratio of weighted clicks to total weights, which normalizes out propensities and yields a more stable off-policy click rate proxy. The function IPSK merges a result set with the click log, keeps the top k per query, and averages inverse propensity weighted clicks across queries. The printed SNIPS value shows a variance-controlled estimate. Now we will expand to 2 queries and show the end-to-end delta between rankers across queries. This example aggregates inverse propensity-weighted CTR at 3 across 2 queries and reports the net change from switching to the alternative PyTerrier ranker. The data frame clicks2 extends the earlier click log with a second query and per rank propensities. We create queue holding both queries, then compute baseline and alternative results using BM25 transform and A.transform. The helper IPSK merges results with clicks, keeps the top 3 per query, and averages weighted clicks across queries for a comparable estimate. The variable D is the alternative minus baseline difference, which we interpret as expected CTR at 3 gain before running a risky live test. The printed delta and decision give a clear go or no-go signal. In a real system, this toy maps directly to a production check. Use your real query set in place of the 2 queries, log several thousand impressions, and compute IPS and SNIPS over the same top K. The mechanics do not change, only the scale and the care you take with propensity estimation. Recap. What it is: counterfactual evaluation uses inverse propensity weighting to estimate how a new ranker would perform from logged clicks. When to use it: when you want a low-risk pretest of a ranking change before doing an A/B test. One caveat: IPS can have high variance when propensities are small, or when the new ranker shows many low prop items. Next step: tune the BM25K1 and B values and recompute the IPS and SNIPS estimates to see how sensitive your decision is to those retrieval parameters. If short, practical IR helps, subscribe and watch the IR videos.